Hello, today we will be solving this problem called counting tilings. So our task is to count the number of ways we can fill an n by m grid using 1 by 2 and 2 by 1 tiles. So we will be given the width and the length of the grid. Notice that the width is pretty small, it is less than or equal to 10. And we need to output the number of possible tilings modulo 8,000,007. So let's head to the drawing board to see how we can solve this problem. So just to make sure we are on the same page, let's consider this example of a grid of size 3 by 4. Then a possible tiling would be to use only horizontal pieces. Another valid tiling can be the following. So our goal is to count all the possible tilings for a grid of a given size. Let us just recall that the width of our grid would be less than or equal to 10. So this should be our point of attack. Let's consider what happens for various cases of n. For example, if n is equal to 1, then we will have a simple line of length m, and we would like to know how many possible ways are there to tile this line. Obviously, we cannot use the vertical tiles, so our only option is to use these horizontal tiles. And there is only one way of putting these horizontal tiles, and the answer does not always exist. Precisely if m is odd, then we cannot tile it with 2 by 1s. Therefore, for n equals 1, there are two cases. Either there are 0 tilings if m mod 2 is equal to 1, or there is 1 tiling otherwise. Great. Now let's consider what happens when n is equal to 2. In this case, we will have the following grid. Now I invite you to consider this particular point here. In a valid tiling, this tile should be covered, and there are two possibilities. Either it's gonna be covered by a horizontal tile, or it is gonna be covered by a vertical tile. If it is covered by a horizontal tile, then we will have something like this, and the tile below it will have only one possibility. We cannot put a vertical tile here. So here we should put a horizontal tile as well. And if you notice carefully, this gave us a recursive approach to our problem. So in the beginning, let's say that we wanted to calculate the answer for n. So in the case where a horizontal tile is placed on this tile, then the problem amounts to finding the number of tilings for a smaller length, this one of length n minus 2. So basically, if we choose to put a horizontal tile on this last tile, then the number of ways will be equal to the number of ways for n minus 2. Similarly, if we choose to put a vertical tile here, then the problem will amount to the same thing as finding the valid tilings up to this position, which is m minus 1. So in this case, the number of valid tilings will be equal to the number of valid tilings for m minus 1. And since here we have a choice of putting either a vertical or a horizontal tiles, then the number of ways for m will be equal to the sum of these two possibilities, because we can choose either of them. So this should be equal to the number of ways of m minus 1 plus the number of ways for m minus 2. Does this ring a bell? Well, this is precisely the same thing as the Fibonacci recurrence relation. And let us just calculate the base case here. So if m is equal to 1, there is only one possibility, is just to put a vertical tile like this. And for m equals to 2, there are two possibilities. So we can either put two horizontal tiles or two vertical tiles. So the number of ways for 2 is equal to 2 and the number of ways for 1 is equal to 1. So this formula combined with the initial conditions we just mentioned, the number of ways for 1 equal to 1 and the number of ways for 2 equal to 2, can allow us to solve this problem for very large m. Great, so now you might be asking yourself if we can manage to find the recurrence relations for like this for larger values of n, for example for n equals to 3. So we will proceed in the same manner. Let's consider the tile right here. So we can put a horizontal piece right there. So that's a possibility. So if we put a horizontal piece right there, we have two possibilities for what remains. For the tile beneath it, we can either choose to put a horizontal tile or a vertical tile. So if we choose to put a horizontal tile there, then the last tile will be predefined and it will also be horizontal. And in this case, we have some kind of relation with the number of ways with m minus 2. But again, for the second tile right here, we do not have to pick this. We can also choose to put a vertical tile here. So another possibility would be to put a vertical tile here. So now we have to consider this tile. We can either put a vertical tile there, and again it would give us some kind of relation with m minus 2, or we can put a horizontal tile here and another horizontal tile there. And in this scenario, we do not have a recurrence relation with another state of the problem, but rather for this last layer here, it is not full. So we're not dealing with the same problem. Basically, this would relate to the number of ways of grids of length m minus 2, where the last layer has this configuration. This one is empty, this one is full, and this one is full. So what I am trying to get at is that for larger values of n, we do not have a clear-cut relation with some problems of the same problem, but rather we have relations with other states where the last layer may not always be full. But what we can be sure of is that we only have to consider two consecutive states. I mean by this, if I am at this actual position, anything I do here, any kind of tile I place here will only affect the next column. So to make things clearer, I will only consider two columns like this for the case where n is equal to 3. And my claim is that we can transition from a given column with a given state to the adjacent column with a different state. So what do I mean by a state here? It is actually the configuration of this layer right here. And as we saw with previous problems, the width of our grid is only up to 10. So we can use the concept of bitmasking to represent all the possible states of a column with only 2 to the 10 values. And for each tile here, we can say whether it is full or empty by placing either a 1 or a 0 there. So in our actual case, n is equal to 3, so we would only require 8 values to represent all the possible states. So in the beginning, we start with an empty column here. So we are at column 0 and all the cells are empty. So the mask for this would be just 0, 0, 0 or 0. And now I will ask myself how I can fill this column. One way to do so is to put a vertical tile here and a horizontal tile there. Great. Now I managed to fill this column and I can transition to the next column, but with which state? Because remember, I have to recall what was the configuration of the next column, because next time I will have to process it. And as you can see here, if we represent this in binary, this will be 0, 0, and this 1. So 100 in binary is 4. So this means that I can transition from column 0 with it being empty to column 1 with it having this configuration. So that would be represented by the state 1, 4. I know that this idea can be counterintuitive, that's why I prepared the following animation so you can visualize the process. So let's consider the following grid. It is a 5 by 4 grid, and as I explained, we will process each column and see to which other states we can transition. So let's consider the first column. So initially the first column is empty. That's why we start with the mask of all zeros. You can notice here that I represented the mask with 5 zeros because I have 5 tiles or 5 bits to represent. And since there is one way of leaving the grid empty, so the number of possible tilings for this configuration is 1. Now for each tile, I will try all possible ways of filling that column. So my first choice is always to put a vertical tile first. So this way I manage to fill the first column, and the second column is also all full. So its mask will be all ones. And now I have to increment its count by 1. Now I will backtrack and see that I can put a vertical tile there. So I get a new bit mask with 3 ones at the bottom and I update it with 1. And I carry on like this. So these are all the possible tilings of the first column. Now I can consider that the first column is full and process the masks I just generated from column 0 to column 1. So this is the first mask I created. It has a full spot on the first tile. I will backtrack again through all the possibilities of filling this column, and it will help me generate the next mask for the following column. Notice that the value here was already not 0. Next, I will process the next mask. The first 3 tiles are already occupied, so I only need to backtrack through the 2 last tiles, and it will generate 2 new transitions. This is the last mask for the first column. So now we've processed all the masks for the first column, so we can transition to the following column and consider that the first column is all full. So the first mask is all tiles being empty. I'll go ahead and speed up this process. See you in the last column. Great, those were all the masks for column 2. Now we will move on to the final column. And this time, instead of projecting what will happen in the next column, we should only consider masks that can be filled with vertical tiles, because if we use a horizontal tile, we will get out of the grid. I will leave you with the animation. This is the first contribution to our final answer. This bit mask is also valid and it will contribute 15 to the final answer. Another contribution of 11. Notice what happens with this mask. We cannot fill it with vertical tiles, so it's not valid. Another contribution of 10. This mask is also not valid. Another contribution of 10. Another contribution of 11. And for the final mask, all ones, for a final contribution of 8 and a final answer of 95. So as we saw in the animation, we can easily solve the problem with dynamic programming and bit masking. So let's call our DP array tilings. It will be of size m, and its second dimension will be of size 1 shifted by n to represent all the possible states for the columns. We will start at the state 0, 0, so we are at column 0 and all the cells are empty. There is one way of doing this because there is one empty grid, and then we will iterate over each tile. We will iterate over each tile and try to put either a horizontal tile there, and that way affecting the mask of the next column, or we will put a vertical tile there if the tile below it is empty and we are not on the last tile, or if this tile is already full, we will just skip it. So each way of filling a column leads a next mask that represents the mask at the next column. This way we can solve the problem in a total complexity of m times n times 2 to the n. So this is pretty much it. Let's go ahead and check out the solution. So this is our solution. I will start by making n and m global variables because I will need them in my recursive function. Then I will define my DP array. As I said, I will call it tilings and it will be of size 8001 because as you will see in the implementation, I will actually need to go one entry beyond the limit of 8000. And the second dimension is just 1 shifted by 10. I will also define my mod as a constant. Next, I will read the length and the width of my grid. I will initialize my tilings at 0, 0 with 1. Then I will loop over all possible columns, and for each column I will loop over all possible masks, and if that mask is greater than 0, which means there is a way to reach that specific configuration, then I will try to fill that column. And in order to do that, I define this recursive function. So my breaking condition is when my index is at n, basically I've filled the whole column. And in this case, I will propagate the number of ways of my current masks to my next mask in the following column. Then I will just return. Otherwise, I have to check if this actual tile is full, and the way to do that is just to end the current mask with 1 shifted by index. Index is my actual position in the column. If it is full, I will just skip to the next index. Otherwise, there is always a possibility to put a horizontal tile. So that is represented by this. I can transition to the next tile, but I have to make sure to turn on the bit for the next mask. And the way to do that is to use OR. The second possibility is trying to put a vertical tile, but that's only possible if my index is strictly less than n-1 and the next tile is empty. Notice the not here. And in that case, I can skip 2 tiles and I do not have to update my next mask because nothing goes into the adjacent column. So after defining this function, I can just call it for each mask that is greater than 0, and at the end my answer will be stored in the tilings of m with a mask of 0. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.